Hi, my name is Chris Moran, and today I'm going to be talking a little bit about some exploration that I've done with applying Rust to the robotics domain. So a little bit of background on myself. Over the past 6 months or so, I've been working as an independent researcher. But before that, I spent a few years working as a research and development engineer at the UC Santa Barbara Earth Research Institute, primarily working on maritime robotics, as well as underwater instrumentation. I think unlike probably a lot of people that are in this group, I actually started doing robotics work and actually programming in general during my senior year of college. When I was doing an internship at iRobot. And so my background is actually in mechanical engineering, which is meant that a lot of my programming experience has been sort of in a practical application in terms of just trying to get something done for manipulating systems that I've been working with. Based on that experience, I've sort of started branching out a little bit, where I have a contributor to the Rust machine learning working group, doing some work on a project called Lympha, which is sort of a Rust version of scikit-learn, as well as contributing to a number of personal projects, one of which I'll be talking about today called Bissel. So I don't think that I need to get into a ton of background about what Rust is as a programming language, considering the group that I'm talking to today. But at a high level, let's just kind of go over to a reminder that it is a strongly typed systems language that is similar in speed as well as expressiveness to C++, but with a lot of compile time guarantees around typing, memory safety, and parallelism. Stability is a big thing in the robotics domain because it involves, as well as aerospace, because it involves a lot of questions around stability of both the language itself as well as dependencies and how well it's been tested. So the fact that Rust is now being adopted by hundreds of organizations and finding a niche in performance critical or mission critical code is something that is going to be highly considered for the adoption of Rust in those industries that might otherwise be somewhat slow to take advantage of it. So why should the real question that we're trying to answer here is why should organizations that are not currently using Rust think about using it in domains like robotics or aerospace? So the big one of these is that most memory-safe languages require some kind of garbage collector. This can lead to both slower code in general, but also lead to latency spikes in code that does things like networking, which is hugely important in robotics because those systems tend to apply something called soft real-time systems approaches. Which means that it's not hard time in that it's not deterministic, that a certain process is going to finish at a certain time, but there is an expectation around boundedness of when a certain operation is going to happen. And so because a garbage collection can lead to these kind of latency spikes that are often not necessarily predictable, that becomes a much bigger issue. And as a result, a lot of code that is written in these areas end up being written in a language like Ada, C, or C++. The second part of this is that languages that are written, is that the use of languages like C and C++ lead to a lot of software vulnerabilities. We're about 70% of critical software vulnerabilities that have been found in code analyses by both Microsoft and Google across fairly large code bases. About 70% of those are due to memory safety issues, which are eliminated through the use of a language like the safe subset of Rust. And I think that this is really critical, in part because obviously memory safety bugs are not great, but in part because those organizations are not hiring people who don't know what they're doing. A lot of those code and those vulnerabilities due to memory safety issues are being written by developers that are writing code full time and that may have a background, a formal background in computer science and that have large organizational resources and processes built around trying to create high quality code. Where in the reality of the space in the robotics and potentially even aerospace domains is that the engineers working on that code are not necessarily full-time developers. A lot of them have backgrounds in something other than computer science, where they've spent a lot of time doing things like control systems. So instead of being able to debug a seg fault or a memory leak using Valgrind, instead they're focusing on trying to figure out a stable control system using Bodhi plots. And so one of the reasons why I think that Rust is very attractive is that it's able to prevent a lot of classes of bugs at compile time without incurring that kind of runtime penalty that you would see with other more accessible languages, but at the same time enable developers who might otherwise not be able to write code for these domains to do so in a way that still enables them to put code in production without necessarily having to add additional layers of having a domain expert talk with the software developer and go back and forth, and instead integrate those two processes and teams a little bit more directly. And so in the robotics domain in particular, this is really important because almost every single robotics middleware and framework is currently written in C++. So if you were to start right now and think about trying to build a robot in a greenfield project, you would almost be certainly considering a framework like ROS or the robot operating system. There's actually two of these, ROS, which is ROS1, and then ROS2, which came out about 5 years ago with some improvements, but both of which have bindings to Python, but are written under the hood. And for, in my experience with using these in critical domain, in performance critical domains, almost always drop back down to C++ whenever it's useful. There's other frameworks like Moose IVP, which was developed at MIT in 2004, and has been running both on primarily in maritime vehicles, as well as, but has been applied to drones, both in industry and academia for research projects, as well as often in military projects as well. And so those are two examples, along with other frameworks like YARP, that are much more focused on robotics domain in particular. But there are other middlewares like ZeroMQ and MQTT, which are sort of more generic IoT ways of sending data back and forth and doing inter-process communication, which is really the fundamental role of most of these frameworks for building these kinds of systems. So just quick side-by-side, we're going to look over a little bit of code that's been written in C++, a little bit of code that's written in Rust, and compare them about the bugs that could potentially occur and how Rust helps to prevent some of the more common errors that you might see while writing C++ code. So here we have a little bit of code that does something fairly simple, where we're allocating an array of values, and then we're filling it, and then we're trying to basically sum all the values in that. And so looking at this code, if you know C++, you're probably seeing at least a couple issues right off the bat. First of all, we're allocating an array of floating point values, but then we're filling it with integers. We have an off by one error that's very easy to see in our second loop. But the truth is that this program compiles just fine. But if you run it, and if you run it 10 times in a row, you'll end up seeing that we get some weird behavior, which is undefined behavior. And this is something that is very, very problematic in the robotics area, because at a high level, bugs in robotic systems don't necessarily lead to systems crashing and then rebooting. They just lead to systems crashing into the ground or into the floor of the ocean. And so we really, really want to try to prevent any kind of errors like this from slipping through. And so the fact that this compiles at all is somewhat problematic. But in addition to this compiling, once we do run it and we read past the end of the array that we've allocated, we're actually reading out of bounds memory. And then we get inconsistent results, some of which are actually correct. If you look at those results where I ran this code 10 times in a row, 4 out of the 10 times, we get the right answer, which means that this code could potentially pass unit tests, or at the very least, cause developers to spend a bunch of time working on trying to figure out what the heck is going on, or potentially make it through those unit tests and into a vehicle, which is not a great thing. In Rust, first of all, off the bat, we do need to cast our integer into an F32 even to put it into that array. But every time that we try running this code, because we're reading out of bounds memory, we're going to panic every single time. And so even though runtime panics are not great, we don't necessarily want those to happen. It makes it much more difficult for code like this or for errors like this to get past unit tests and into production code. And so at a fundamental level here, Rust claims to be a language that empowers everyone to build reliable and efficient software. But the real question is, at least to me, is that could it help to make this true, particularly for the robotics domain, to make writing code for that area and in mission critical code, make it more accessible to people that would not otherwise be able to write code for those areas? So to explore this, I started working on a personal project, which is an experimental robotics-focused middleware called Bissel. I don't have a cool logo yet, but we'll get there. So this project is mainly focused on developer ergonomics, ease of use, and transparent design with all of the benefits of Rust, like parallelism and type safety and memory safety. It's largely targeted for use on modern embedded systems with a large focus on ARM single-board computers. A really big reason why this is important is because of the increasing use of computers like the Raspberry Pi in modern robotic systems, even if they're not initially top of the line, but ones that are really becoming functional and widespread throughout this area. It uses a star-shaped network topology, which is something that we'll get into a little bit later. And it takes inspiration in its both design and operation from ZeroMQ, MoosIVP, and ROS2, which are projects we mentioned earlier. I do want to add the little bit of a caveat that this is probably not ready for serious use at the moment. It's still highly experimental. The code is on crates.io as a 0.2 release, but I'm also in the middle of a big rewrite right now for adding features like UDP support and a little bit of an API. So this is, at a high level, what a Bissel network looks like. So we have a host in the middle. We have various nodes that are along the edges that can take various states. And they're strongly typed, and then they can send messages back and forth. So we don't need to get all of it into this right now, as I'm going to explain some of the details, but I did want you to have a little bit of an image of what's going on in your head. So under the hood, Bissel is using a number of programs. This is actually somewhat, if not unique, been important to note, because for some projects like MoosIVP, they explicitly advertise, so to speak, that they are zero dependency, or that they don't pull in third-party libraries. And that's important in the robotics domain because end users want to be able to understand where their code is coming from. Being able to verify the relationship of that code is very, very important. And so in this case, all the libraries that I'm using, I'm not just evaluating based on whether or not they work for my specific case, but the likelihood that they'll be available and stable in the future as well. And so the first of these that I'm using is SLED. Which is a high-performance embedded thread-safe database. That's very similar to a B-tree map that's operating on Robotics. It was developed by someone named Tyler Neely, who has both written SLED as well as another library called Rio. And he has a bunch of great talks and writing about building and often breaking stateful distributed systems. He's also got quite a few numbers of sponsors on GitHub, which Lacho alluded to earlier. Which is, to me, something that's very important because it implies something about the reliability and the likelihood that this code will be maintained into the future. It's also got a pretty active Discord and developer community, which is important to that as well. I don't know how familiar everyone is with the Tokyo async runtime. I'm assuming most of you are, but in case you don't, Tokyo is one of, if not the asynchronous runtime in the Rust ecosystem. Basically, it just enables a large number of async connections, which is a huge benefit for especially low resource embedded systems that are trying to talk between a number of nodes. Tokyo does get a lot of support, both from sometimes paid contributors, as well as a number of corporations that rely on it for their own software. And so it's reached 1.0, and so it is supposed to be stable and is receiving regular updates, which makes it suitable for a project like this. The final piece of this puzzle, or the final piece and a half, is Postcard, which is a serializer or a deserializer that is compatible with environments that don't require a standard library and is based on the SERDI project. SERDI is really foundational because it allows us to basically to serialize and deserialize data in a structured way and pass it back and forth between nodes in a way that also allows us to take advantage of a lot of the type level advantages that Rust provides through the type system without having to, while being able to take some of the uncertainty that we would have if we were simply operating on stringly typed or byte level data and to get rid of them. So we're going to talk a little bit more now about the hosts, which is the central coordination process of a Bissel network. Under the hood here, it primarily uses an async TCP listener, which spawns connections and then transmit messages back and forth between the host and the nodes using something called the generic message, which stores a data payload as a vector of unsigned integers and has both a topic, which is the name of that particular type of data, as well as a message type, which allows us to set or get a message into the SLED database, into the key value store there. And so if it's a set, it simply stores that data in that message under the topic name. And if it's a get, the database will check to see if there is an entry. If it exists, it'll add that to a message, format that, and send it back to the node. The nodes themselves are the primary thing that most users are going to be interacting with when they write Bissel code. They're strongly typed, which is really important because it helps us to eliminate certain types of bugs and operations and take advantage of the ROS type system, again, to sort of prevent some potential errors around the statefulness of our system. So nodes primarily have three potential states at any given time. When they're first instantiated, they're considered idle. Then you can either use a connect method or a subscribe method to create an active node, in which case you're able to basically on demand in your code send a publish or request to your host, or have a subscribed node, which basically loops over pulling requests, which allows you to always have the most recent information that the network itself has on a given topic, and store that internally so that it can be accessed by your process without necessarily needing to deal with some of the latency that might otherwise occur if you were trying to have on-demand connections. I hope that that bit of an overview gives you a little bit better of an understanding of what the topology of that network and the behavior of these networks are going to look like over time. So what we have here is just a little bit of code that puts together a pretty simple Bissel network. I realize that there is like a lot of characters on the screen right now, and I'm not expecting everyone to look through this. But I do hope that it gives you a little bit of an idea of what the code will end up looking like in terms of a final API for developers that choose to use it. And one of the big things here is that you can basically use Rust, despite it being a systems level language that runs very, very fast. You can use it in a way that reflects some of the more ergonomic code that you would write using other frameworks in Python. And so using Rust as a language helps developers to bridge that gap, where you can both write low-level, very performant, very specific code that can be highly optimized, but I'll also have available high-level APIs that allow developers to basically code and script behaviors at a high level as well. I do want to draw your attention to, if you can see it down at the bottom, there's two lines down here that really kind of help to demonstrate why static typing and including state information in the type system helps us to prevent some errors. Well, for example, we up at the top created a node that is typed as a coordinate data like you would pull from a GPS, and then we are trying to publish a usize value. And if we try to do this, we will get an error at compile time, not at runtime, which means you don't need to deal with some of the error handling around that, and helps us to prevent potentially name mix-ups or namespace mix-ups that could otherwise become an issue. So moving on to applications, there's two primary projects that I've been using to sort of dog food the construction of this system. The first of which is called Turtlesim, which is an introductory robotic simulator, primarily used in the ROS ecosystem. And so I went about trying to build a clone of this. And so the turtle on the screen, which is created in an app that we'll get to a little bit afterwards, can be controlled using arrow keys, or it can be scripted from an external program. Where the script in the external program is reading in the turtle's position and then sending user input or simulated user input to control the turtle. And I think that this is interesting in large part because it addresses some of the primary requirements for building higher level autonomy. Including white space, the total script for the motion that you're seeing on the screen there is under 65 lines of code, which includes the instantiation and connection of two nodes to the host, as well as the actual behavioral code itself, which is, lines of code are not a perfect metric for estimating simplicity of a given program, but it's not a good metric for that either. The app itself is built using the Bevy game engine, which we'll also use a little bit later on for our other project. It's a data-driven architecture, it's open source license, and it's currently being developed by the lead developer full-time. He used to be a senior software developer at Microsoft, but has quit that position and is now working on Bevy full-time, while being sponsored by several studios and having a number of independent sponsors as well. All of which is to say that using Bevy as a base, which is also pure Rust, has the benefits of also some stability in terms of the likelihood that it's going to be an available platform in the future. One of the things that I was really surprised of when building this application was how easy it was to integrate Bissel with that game engine. I did not start building these applications simultaneously. And so basically, in order to use Bissel and integrate all of the data structures pretty seamlessly into the Bevy game engine, basically required 4 lines of code, 2 of which were simple derived statements using a macro that was built into the Bevy library. And so that was something that I was really pleasantly surprised with as a development experience. Moving forward, this example here was pretty simple, but there's definitely some improvements that can be made. Bevy has a plugin for the Rapier real-time physics engine, which is, again, professionally maintained by the DIM Forge organization. It specifically lists robotics as a potential use case and has associated collision and linear algebra libraries, as well as deterministic physics that can potentially be used to develop much more realistic and autonomy operations for potentially more complicated situations in the future. For example, by building not a one-dimensional or a two-dimensional turtle that's moving around, but if you wanted to develop something like a drone control system, that would be definitely a way forward. I'm also going to be working on doing some PID controller integration and waypoint autonomy, because waypoints, in my experience, form the basis for a large number of autonomy operations. And so being able to build a control system that can develop those is a pretty important part of building out the capabilities of a system like this. The second application that I want to talk about is something called orientation, which is reading in the input of a BNO055 Bosch absolute orientation sensor, which is basically an inertial measurement unit, and streaming that to, again, a Bevy app to display that information in real time. The entire stack for this project is written in Rust. So the driver that we're using to read in the data from the IMU board itself, the program that is running on the board that is communicating that information, as well as the one that is receiving it and running the simulation on the host laptop. This is Rust all the way down. And so the board itself is an Odroid C4 Linux single board computer. It's very similar to a Raspberry Pi, except it's a little bit more powerful, and it's got some extra peripheral IOs like PWM signals, which is pretty nice. It can also pull in a 5.5 to 13 volts on the input voltage, which doesn't necessarily seem like it's super advantageous until you realize that by having that, you can actually just plug a 3S LiPo battery that you often find for remote control projects directly into that board computer without needing an inline voltage regulator. So the IMU itself operates at 10 hertz, and basically we're sending those updates directly to the laptop itself, which is the reason why, if you look at some of the lag that's going on there, that's the reason for that, is because we're not interpolating the values themselves as they go. The IMU connection, as I mentioned, is over I2C through the Linux embedded health rate, and then it's being streamed over a 2.4 gigahertz Wi-Fi network through a router that's off the side of the screen to a Bevy app, which again is wrapping Bissel. On the board side, we're basically pulling in that information, then we're applying a transformation and converting it from an Euler angle in the math interop system or MINT library into the CLAM library, which is a linear algebra library that Bevy uses natively, and then just simply publishing it with one line. If we weren't going to be applying that reference frame correction, we could actually just use the .into method, which I think is pretty interesting because it demonstrates one of the really great aspects of the Rust ecosystem as it stands at the moment, which is great interoperability between a number of libraries. In the same way that because we're using postcard to serialize and deserialize using SerDes underneath the hood, both the MINT library and the CLAM library already implement SerDes. And so it doesn't require any additional work on our part to make that happen, just to call out cargo.tell file. Big thing here is that, of course, the dev computer that I was working on was on x86, but the deployment computer that we're using here was on ARM64. And so this is a huge deal in the robotics space at the moment. And this is actually my favorite slide of this entire presentation. Because on the right-hand side, you have the directions for cross-compiling code using the ROS framework. And this is ROS2, which is actually more ergonomic than ROS1 in terms of its build systems. It takes about 20 seconds to scroll down that page, requires setting a bunch of environmental variables, and is generally pretty complicated in itself. For compiling Bissel and deploying it to either the Odroid C4 or a vehicle like the Blue Robotics Blue ROV2, which is a vehicle that I have deployed Rust code on in the past, it's 3 lines. And that is a huge benefit to developing code in robotics for robotic systems in Rust, because the cross-compilation capabilities and the ergonomics, therefore, are huge time savers. We've already talked a little bit about what's going on the top side computer, but in this case, the big thing that I want to call out here is that the app itself is, again, about 127 lines of code, and is pretty simple to grok. And so building complex systems like this that may be more difficult in other systems, because of the libraries that are available in the Rust ecosystem that have pertinence to Rust availability, I think that there's a lot of promise there. So what wasn't so great? There are definitely some rough edges. I did find an example of, even though there were 2 libraries that were supposed to be sturdy compatible, they weren't. The dependencies can stack up pretty quickly, and the device libraries may not be fully tested, like when I was trying to do this with GPS, but found an error while working with some coordinates. So just to wrap up pretty quickly, in summary, Rust is great in mission-critical domains because it can help catch a lot of potential errors of compile time. It helps prevent undefined behavior, and it adds the option for writing complex code like concurrent code, which is going to be critical for next generation companion computers running for a highly autonomous vehicle, as well as having excellent cross-compilation support, and a library ecosystem in the open source community that has pretty strong foundation. And so all of that combined, I think that developing robotic software in Rust could offer some really meaningful benefits, both for experienced developers who have spent time working in these domains, as well as newer programmers who don't have the experience to potentially work in languages like C and C++, in order to contribute to projects in these areas. So with that, I think that's the end of this presentation, and I'm happy to take any questions.
Thank you very much, Chris. That was an incredible talk. Any questions from in the room, and then we'll go to online. Question? Yeah.
Thanks for having me. Just curious how you're doing tracing with robotics. I noticed you had to begin with some errors you wanted to capture, let's say with some C++ code. If once you deploy this onto the Pi or the Odroid, how are you getting telemetry off that, and can you do that real time, or do you have to go and explore some logs on the device itself?
Sorry, I'm not sure what you mean when you say tracing. In terms of pulling telemetry about what's actually happening in the app off of the companion computer?
Okay, more generally, how would you debug problems on the device? And let's say, I mean, in my experience building like services on servers, not on robotics, I would have tracing in there, so I know every request response, what the actual payloads were back and forth, so I would log that externally as well. I was just wondering if you have a similar thing with robotics, or you have like some ideas of how to do that.
Yeah, so in general, we do build a bunch of log files in place on the robotics computers. And so for that, in this particular instance, because I'm using the Tokyo library and ecosystem, Tokyo has a tracing library, literally called tracing, that allows you to build log files and develop pretty good ways of sort of understanding that behavior on that client side, as well as comparing those via timestamps on what we're receiving on the host side. Does that answer your question?
Great. We have a question from the chat. Awesome talk. As someone who does not have a formal computer science background, how was your experience learning Rust with its notoriously steep learning curve?
So actually, Rust was, I basically started writing Bash. And I literally, my first project writing not just robotics code, but basically any code, since I took like an introductory MATLAB class my freshman year of college, was about pulling logs from a robot and pulling those logs off of it and automating basically that log pipeline. And so I pretty much jumped right from writing Bash code and a little bit of MATLAB into Rust. And one of the reasons I was able to do that was because the documentation for beginners is absolutely superb. And so I think that that's a huge benefit where I'll think a lot of Rust programmers, because they want to jump into doing things like writing macros or jumping straight into doing generics, that sometimes they miss the forest for the trees a little bit, where just getting started with writing any Rust code and then expanding your capabilities from there, because of the documentation and because the compiler is super helpful, I found that to be, as someone without a lot of programming experience, to be a really, really great experience.
Great. Oh, yep, we got another question. I'm gonna have to chuck this over, so bear with me. Oh, you know what? Let's just keep it health and safety.
Can you hear me?
Mm-hmm.
So first, brilliant talk. I love this. Second thing, quick question. Have you considered deploying this project on a device that doesn't run a Linux kernel? Like, because I don't know, a robotics seems to be something very delicate, and having a complete system just throwing a tantrum after one too many apt get just seems a bit dangerous. Have you considered like something Arduino or something even lower level that you don't have a kernel, just this is your Rust code, do this?
Yeah, so there's definitely some considerations on that end. So the primary code that I would consider deploying to a device that doesn't have basically the full Linux baseline with regards to allocators and standard libraries and everything along those lines would be for a node, right? That's the base level. Is we're probably reading in something in real time or receiving information in real time, and then we want to either write telemetry or write a control signal somewhere else. And so I don't think that I could take the code that is currently in the Bissel in this project and use that directly in an environment that doesn't have a standard library. However, Postcard itself is available without necessarily needing an allocator, but you can use the alloc crate to do that, as well as libraries like, I believe, small TCP, SMOL, which carries which is also an LSTD compatible library. And so I think that you probably could do that, but the main use for a system like this, and frankly for a lot of them, is in companion computers, which sit sort of in a backseat driver configuration. So they're running a full Linux system, but the flight controller that is handling the real-time, got to run this control loop at 50 hertz per second and pull in information very quickly, that tends to be running on a dedicated, like an STM32 microcontroller itself off the board. And then they're communicating over serial or some kind of other network layer.
Great. Oh, have you got any follow-ups? No? All good? Great. Thank you very much, Chris. Any more questions? Any more questions from the chat, Giles? Great. How important was your mechanical engineering background in, what was the rest of it? In robotics and Rust?
I think that so far for this project, my mechanical engineering background has helped with regards to dealing with like the orientation in terms of dealing with, let's see. The concept of objects rotating in space is really important in mechanical engineering. And so those are typically used with regards to tensors and other mathematics that are and other linear algebra concepts are both heavily overlapped in controls and in computer science. I actually think that most of my mechanical engineering expertise, or expertise is a relative word, of course. Most of that experience is going to be helpful a little bit further down the line once I start doing things like trying to implement waypoint controls, because control theory like PID controllers and tuning those and building systems like that, which tend to be a little bit higher level than most of the work that you saw in this project. That is work that is in my experience, pretty core to a lot of mechanical engineering curriculum, but is not work that I've implemented thus far in these projects, but I'm expecting to end up being pretty significant down the line.
Great, thank you very much, Chris. Please give him another big hand.
Thanks, everyone.
And we want to see more of what you're doing in the future, man, because this looks like a really, really cool project. So we're going to keep in touch. I'm going to keep updated with everything you got going on.
Sounds great.
Great.